This is our framework, and we're going to try and draw the shear force and bend moment diagrams for this frame. The first move, however, is to calculate the reaction forces. And before we start to do looking at any of the members or the joints, we need to work out the reaction forces, and for that we must draw a free body diagram replacing the supports, the fixed support at A, the roller support at D, with the associated forces. At joint A, it's a fixed support, so replace that with two forces. I'll label that VA and HA. And at the support D, it's a roller support, so replace that by one force labelled VD. Draw in the other applied forces. So we have 10 kilonewton, we have 40 kilonewtons, and 20 kilonewtons, and 15 kilonewtons, and a UDL along the top of 20 kilonewtons per meter. All the dimensions that are used are back in the initial diagram. Now we can calculate the values for our reactions. To do that, we apply the three basic equations for equilibrium. All the forces in the x direction add up to give you 0. All the forces in the y direction add up to give you 0. And for equilibrium as well, all the moments about any point must add up to give you 0. Considering the first of these three equations, we're looking at all the forces going horizontally. Remember the sign convention. So forces going to the right are positive, back to the left are negative, going up is positive, and going down is negative. So looking at all the horizontal forces, we have HA positive, plus 10, plus 40, minus 20, minus 15 equals 0. Adding all the numbers parts together, we should get HA plus 15 equals 0. Rearranging the equation, we get HA is equal to minus 15 kilonewtons. There's your first reaction force worked out. Now considering forces in the vertical direction, forces going up or down, we have the two reaction forces going upwards, VA, which is positive, plus VD is also positive, but then we have the UDL acting downwards, 20 kilonewtons per meter for 6 meters of it. For equilibrium, these must add up to give you 0. Rearranging our equation, VA plus VD minus 120 equals 0, or the two reactions must add up to give you 120 kilonewtons. If we know the value of one of the reactions, we can easily work out the other one. Now applying the third equation for equilibrium, moments about a point. Remember, moments is a force by a distance. For moments, it's clockwise moments or anti-clockwise moments. Clockwise moments are positive, anti-clockwise moments are negative. Also, for moments, we must specify the point we're actually taking moments about. We usually do that about the first support, and in my diagram that was labelled point A. Shorthand notation is A with a little bent arrow over the top. That details that I'm taking moments about point A. Looking back at the diagram, here HA and VA are applied at point A. There's no offset distance, so those two reaction forces don't produce a moment. What does produce a moment are the other forces, the 10 kilonewtons, the 40 kilonewtons, the UDL, the 20 kilonewtons, the 15 kilonewtons, and VD. For each of these, we're going to work out the moment. Remember, the moment is the force times the distance. Then we must consider whether they're positive clockwise or negative anti-clockwise in rotation. For the distances, most of the distances are relatively straightforward. From point A, 10 kilonewtons is 3 meters away, 40 kilonewtons is 6 meters away, and so forth. But we'll consider each one in turn. For the first force, remember HA and VA don't apply. We have 10 kilonewtons, and the distance to the 10 kilonewtons is 3 meters, and that distance is the distance from A up to 10. Next force we'll consider will be the 40 kilonewtons, and the distance involved is again from A all the way up to the 40 kilonewtons, and that will be 6 meters. Now, dealing with the UDL, what we do is we take all of the weight of the UDL and concentrate that as a point load in the middle. So effectively what we have is 120 kilonewton point load in the middle of the UDL. So that's the size of the force. However, when we're considering distance, it's the force times perpendicular distance to line of action. So if we take our force, dot that down, what we're looking for is the perpendicular distance from A to the line of action of the force, and that would be 3 meters. The moment for the UDL will be the size of the force, which is 120, and the distance to the line of action is actually 3 meters. Next one we'll consider will be the 20 kilonewton force. So take the force, carry it across, and looking for the perpendicular distance relative to point A, and you can see here it will be all the way up, and that should be 6 meters. Next force, 15 kilonewtons. Right, take that force, carry it the line of action across, and we're looking for the perpendicular distance to get relative to point A, and you can see from point A we'll go up a distance of 3 meters. Then finally, the last force to produce a moment is the force VD, and the distance relative to point A will be 6 meters across. These moments must all add up to give you 0 for equilibrium. We have each of the moments worked out. We now need to consider whether they are positive clockwise rotation or negative anti-clockwise rotation. Going back to our diagram, remember to do this, you consider the force is on a piece of string. You're holding the piece of string at point A because that's the point you're considering, and you're looking to see how the force would rotate around that point, point A. Does it turn around clockwise or turn around anti-clockwise? So for the first 10 kilonewtons, There's your piece of string. If that force were allowed to freely rotate around point A, it would want to go around in a clockwise manner, and hence would give you a positive moment. Likewise, for the 40 kilonewtons, longer piece of string, if the 40 kilonewtons was allowed to freely rotate around point A, it would want to rotate around in a clockwise manner, positive moment. Similarly, for the UDL, it's concentrated down into a point load of 120 kilonewtons. If that force were on a piece of string and were allowed to freely rotate around point A, the way the arrow rotates, it also wants to go around in a clockwise manner. So the first three moments we have in our equation are positive. Now consider the next three moments. The 20 kilonewtons, right? If that were on a piece of string and allowed to freely rotate, so you hold the string again at point A, how would the 20 kilonewtons want to rotate around point A? It would want to rotate around in an anti-clockwise direction, therefore is negative. Similarly with the 15 kilonewtons, if that were on a piece of string, you're holding it at point A. How would that force carry the force across? How would that rotate around? It would want to rotate around in an anti-clockwise direction, therefore is a negative moment. Similarly with the reaction VD, it's on a piece of string, you're holding the end of the string at point A. How would VD want to rotate around point A? It would want to rotate around in an anti-clockwise manner, therefore a negative moment. Updating these into our equation, negative, 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 then we can simply rearrange the equation and work out our first reaction. Force there should be 15. Bringing the numbers together, we should get 465 minus 6 VD equals 0. Take the 6 VD to the other side and it becomes positive. Then divide through by 6. Gives you VD, and that works out to be 77.5 kilonewtons. There's our first reaction force worked out. Now applying the previous equation, you can see at the top of the page, VA plus VD is equal to 120. Substituting in our value, 77.5, then rearranging this equation, 77.5 goes to the right hand side, we get our other reaction, which is VA is 42.5 kilonewtons. So for the reactions, we have HA is minus 15 kilonewtons, our VA is 42.5 kilonewtons, and our VD is 77.5 kilonewtons. Going back to our free body diagram, we're going to put the reaction forces on, and our VA value is 42.5 kilonewtons. Our VD value 77.5 kilonewtons, and our HA value as calculated is minus 15 kilonewtons. However, for this analysis, we only ever want to deal with positive values. So even though I've drawn in HA as a negative 15, what I'm going to do is I'm going to take it out and turn it around, because the minus sign indicates that the arrow is going in the wrong direction. So I'm swapping the arrow direction round and then putting in the HA value of a positive 15. With that, we can look at our first member. When we're looking at our first member, remember the notation or the orientation we're looking at for the structure is that we're going to analyze it in a clockwise manner. First of all, we're going to start with joint A to do member AB. So whenever we draw down member AB, we draw from point joint A up to, but not including, joint B. Drawing joint A on the left hand side, we should have this is our member, rotating it around 90 degrees so it's horizontal. We should have our reaction forces VA, which is 42.5 kilonewtons. We have HA, which is 15 kilonewtons. We have the 10 kilonewtons applied in the middle of the beam. Now remember, we're only looking at the member, we're not looking at the joint. And you can see the 40 kilonewtons, that's actually applied at the joint and not on the member. So at this point in time, we do not include that. Next stage is to apply equilibrium to this member. So remember, equilibrium equations are that all the forces in the x direction must add up to give you 0, all the forces in the y direction must add up to give you 0, and all moments about any point must add up to give you 0. Doing that, so instead of writing down the first two equations, I'm just going to kind of do it by hand. Looking at forces horizontally, so we have VA, which is going to the right. To balance that, we must have an equal and opposite force going in the opposite direction. For the vertical forces, we have 15 going up, 10 going down, so that it's balanced vertically, we must have 5 kilonewtons going down. And then moments, to balance the moments, what I'm going to do is just put in a clockwise moment at the end of the beam, and we'll apply our equilibrium equation. Alright, remember sigma mx equals 0. Remember, moments is a force by a distance, and we're going to take moments about point A. VA, HA are applied at point A, so they don't produce a moment. What does produce a moment is the 10 kilonewtons, the 5 kilonewtons, and whatever the moment is on the very end. The 42.5 applied at the end of the member acts through joint A, so it doesn't produce a moment. Writing down our force by distances, we have 10 by 3 and 5 by 6. And the way I've drawn in the M at the end of the beam, it's a m value, and it's going round clockwise, so it's a positive m. All these moments must add up to give you 0. Then we'll apply or look to see the 10 kilonewtons and the 5 kilonewtons, the direction. Remember, clockwise moments are positive, anti-clockwise moments are negative. So considering moments about point A, remember, consider the force on a piece of string. You're holding the piece of string at your point A. How does the 10 kilonewtons want to rotate around that point A? And it would want to rotate around in a clockwise manner. Then consider the 5 kilonewtons, same piece of string, slightly longer. How would the 5 kilonewtons want to rotate around that point A? And it would want to go around in a clockwise manner. Therefore, your two sets of moments here are positive. Work this through, so you have 30 plus 30 plus m equals 0. So 60 plus m equals 0, or m is equal to minus 60 kilonewton meters. Now, before we start to draw our bending moment diagram and shear force diagram for our first member, we're going to redraw out this member again and put on our values. Horizontal force 42.5, 42.5. You have 15 applied at the end. You have 10 and 5 applied. Now, the moment that I had drawn in initially, m was clockwise. It worked out to be a value of minus 60. So remember, as we did with the HA value, I changed the direction of the arrow to keep positive values. Likewise, with the moment here that was initially clockwise, the value is minus 60. Therefore, I'm going to swap that round to be anti-clockwise with a value of 60 kilonewton meters. To draw our first diagram, the shear force diagram, I'm going to draw in some construction lines. Show the start, where the force is, and obviously at the end of the beam. Draw around and draw in a 0 line. This is going to be our shear force diagram. All units are going to be given in kilonewtons. Starting at the left hand side, considering the vertical forces, our first force we see on the left hand side is going to be 15 kilonewtons, and that's going to jump us up to a value of 15. As we progress through to the middle of this beam, we're going to stay steady at 15. The middle of the beam, we've got a drop of 10. That will take us down to a value of 5 kilonewtons. Then we're going to stay steady at that value until we come to the very end of the beam, and the 5 kilonewtons on the end will drop us back down to 0. To draw our bend moment diagram, I'll draw some more construction lines down. Draw in a 0 line. This will be our bending moment diagram. The units for this one will be in kilonewton meters. We should start at 0, and if our mass is right, we should end at 0. To get our values we need for our bending moment diagram, you need the areas on your shear force diagram. So first we're going to work out what this green area is. Then I'm going to work out what this area here is. We use these areas to give us the value on our bending moment diagram. First area we have in green is 15 tall, and the distance across the middle of the beam is 3 meters, so that gives us an area value of 45 kilonewton meters. For the blue area, it's 5 meters or 5 kilonewtons tall, it's 3 meters across, so that will give us a value of 15 kilonewton meters. Using these two values, we're going to start at 0. The bending moment value is given by the summation of the area on your shear force diagram. So as we come to the middle of the beam, the total area we have will be 45 kilonewton meters. At the end of the beam, the total area we have on the shear force diagram will be the 45 plus a further 15, and that will give us 60. Our shear force, our bend moment diagram should close off at 0, but if you look at the top of the beam, the top of the page, we have a moment applied at the very end, which is anti-clockwise 60 or negative 60, and that will cause our bending moment diagram to close back down to 0. Now what we need to do is, how do we join the dots on our bend moment diagram? Here we're going to look at the value of the shear force, and that gives you the gradient. So for the first part of the beam, the shear force value is constant 15, positive 15. So what that says is that in this region, the first part of the beam, the gradient here is going to be 15. Likewise, for the second part of the beam, the shear force value is constant at 5, positive 5. So the gradient, or the line in this region, will be a straight line of gradient 5. That's our shear force and bend moment diagram drawn for the first member in our framework. Now let's go forward and consider the first joint. When we're considering our first joint, in this case joint B, we're going to look at the load condition at the end of member AB. This time I've turned it round to the vertical, but we should still have the same load condition. What that means is that we had a 5 kilonewton load and a load of 42.5 kilonewtons. To go with that, we had an anti-clockwise moment of 60 kilonewton meters. This load condition is going to transfer into the joint. Now, if you remember back to the very original problem, we had a load applied at the joint that was 40 kilonewtons. Now this comes into play when we're looking at the forces or trying to balance the forces at joint B. To do this, think equal and opposite. So our 5 kilonewtons, 42.5 kilonewtons, or 60 kilonewton meters will transfer into the joint by equal and opposite. So 42.5 going down means we have 42.5 going up. 5 kilonewtons going to the right means we have 5 kilonewtons going to the left. Anti-clockwise 60 kilonewton meters means now we have a clockwise moment going into the joint of 60 kilonewton meters in the clockwise direction. Now our joint has to be in equilibrium. So now we're considering how the 3 green forces, moments, work with the 40 kilonewton meters to balance the forces in at the joint. Looking at the horizontal forces, 40 kilonewtons to the right, 5 kilonewtons to the left. For our joint to be in equilibrium, we must have 35 kilonewtons going to the left. Vertically, we have 42.5 going upwards. To balance that force, we must have 42.5 going down. For the moments, we have a clockwise 60. To balance the forces at the joint, we must have an anti-clockwise 60. These 3 red forces, moments, will then transfer on to the next member, member BC, by equal and opposite. So red 35 going to the left means you have 35 going to the right when you go into the next member. 42.5 going down means you'll have 42.5 going up. Anti-clockwise 60 moment means then you must have a clockwise moment of 60 going into the next member. Taking these 3 forces, moments, we can take that along with the next member and is considered loading to apply equilibrium and hence work out the forces involved on the next member. Now when we're looking at the next member, member BC, 6 meters long, 20 kilonewtons per meter. The force condition we have on the end, the left hand side of the beam, is that in blue we've taken from joint B. So we would have a 35 kilonewton force going to the right. We have a 42.5 kilonewtons going upwards, and we have a clockwise moment of 60 kilonewton meters. Now consider equilibrium for the beam. Again, we're only looking at the member. We're not looking at including joint C. There's a separate force applied at joint C, and we're not at this point in time considering that load, just whatever is applied at the member. For equilibrium, our member must balance forces vertically, horizontally, and moments at any point. So doing a quick calculation, looking at the equilibrium of forces, 35 kilonewtons going to the right, therefore we must have, to balance that, 35 kilonewtons going to the left. Looking at the vertical forces, 42.5 going up, 120 kilonewtons going down, 20 times 6. To balance that, we need a vertical force on the end of 77.5 kilonewtons. Moments, we'll apply a moment at the end. We'll have to do a calculation to work out what that value actually is. So applying our equilibrium equation, moments by any point. Remember now, this is point B. So we're going to take moments about point B. Moments are forced by a distance. On the very end of the beam, left hand side, we have a clockwise moment of 60. The clockwise rotation makes it positive. Then whenever we're considering the UDL, we put all the weight of the UDL as 1 point load in the middle. The distance across from B to that point is going to be 3 meters. So it's going to be 120 by 3. We'll get a sign in a minute. Something else that produces the moments is the 77.5 kilonewtons on the end. the distance from B across to that is going to be 6 meters. And on the end of the beam in green, I've drawn in a moment. It's clockwise in rotation, the way I've drawn it in, therefore it will be a plus m. All these moments must balance to give you 0. We've got 2 moments left. We need to get a direction for them, remember clockwise or anti-clockwise. So again, consider each force on a piece of string. You're holding the piece of string at your point B, and in this case the 120 point load in the middle representing the UDL is allowed to freely rotate. How does it rotate round? It wants to rotate round in a clockwise direction, therefore is a positive moment. The 77.5 on the end of the beam, again hold it on a piece of string. You're holding the string at point B, slightly longer piece of string. How would that 77.5 kilonewtons rotate around point B? It would want to rotate around in an anti-clockwise direction, therefore is a negative moment. Now doing the maths for it, 60 plus 360 minus 465 plus m equals 0, and we get minus 45 plus m equals 0, or m is equal to 45 kilonewton meters. Now we can redraw out our beam with our applied forces. We now have the moment in place at the end of the beam, and we can draw the first of our 2 diagrams. For the first of our 2 diagrams, the shear force diagram, I've drawn out the beam again with the loads on the left hand side and our calculated loads on the right hand side. Our moment has worked out to be a value of positive 45. It was initially drawn in as a clockwise rotation, so keeping it in that rotation, so I'm only dealing with positive values. First of all, I'm going to draw in some construction lines. Draw in a 0 line. I'm going to draw first diagram, shear force diagram. All the units are going to be in kilonewtons. We should start off our diagram at 0. Considering the forces from the left to the right, our first force upwards gives us up to a value of 42.5. Then considering the forces at the end of the beam, just before you come to the 77.5, you would have 42.5 upwards. Take off the 120, 6 times 20 from the UDL. That would give you a resultant force of 77.5. Just going to keep the construction line going down a bit more. Then the last force we have on the end of the beam, 77.5, that will bring us back and close our shear force diagram back to 0. To join the 2 dot crosses from the left to right hand side, you should know from a UDL that you would get a diagonal line. The gradient of the diagonal line is equivalent to the rate of the UDL. There's our shear force diagram drawn. Now we're going to use this diagram to draw our bend moment diagram. To do this, we need to work out the areas enclosed on our shear force diagram. And to work out these 2 triangular areas, you're going to need the distance across to where your line crosses over the x-axis, i.e. this distance here. Very simple to work out. Take the starting point, 42.5, divided by the rate of the UDL, which is going to be 20, and that should give you 2.125. Therefore, this distance to where your line crosses the x-axis is 2.125 meters. The tire length of the beam is 6 meters. Therefore, this distance will be 6 minus your 1.25, and that would give you 3.875 meters. With that information, half the base times the height, we can use that to work out the green area and hence the blue area. To do the green area, half the base times the height is going to be a half times 2.125 times 42.5. That's going to give you a value of 42.5. So this value here is 45.2 kilonewton meters. The blue area beneath the axis is a half the base times the height. It's going to be a half times 3.875 times 77.5. That really should be negative beneath the axis. That area works out to be a value of 150.2. Note, put in a negative because it's a value beneath, or an area beneath the axis. Using this, with our moments we have, 60 on the left hand side, 45 on the right hand side, we can use this to construct our bend moment diagram. First of all, I'll draw in some construction lines. The next thing for us is to draw the bend moment diagram. So we have our areas worked out on our shear force diagram, and I've drawn in some construction lines. So here we're going to have our bend moment diagram. The units are going to be in kilonewton meters. We're going to start off at 0. And if you look at our diagram, first of all, on the left hand side, what we have is a moment, clockwise moment of 60, and that will cause us to jump up to a value of 60 on our bend moment diagram. To that, we're going to add the first of our areas by the time we come to the crossover point on our shear force diagram. So 60 plus the 45.2 will give you a value of 105.2, which would be about there. Then, considering the total areas we have by the time we come to the end of the beam, so currently at a value of 105.2, we come to the end of the beam, we've got our negative area to add on to that, and that should give us a value of minus 45. Looking at the end of the beam, you can see we have a clockwise moment of 45, and that would cause our bend moment diagram to close back to 0. Now we've got 3 points, and we need to consider how you would actually join them together. To do that, we consider the value of the shear force. Value of the shear force gives you the gradient at any point on the bend moment diagram. So let's consider the shear force value we have at the start of the beam, 42.5 positive. So that tells us we've got a positive gradient at the start of our bend moment diagram. Looking at the shear force value here, we have a 0 shear force value. That means we have at that point a value of 0 gradient, or a flat line. Then at the end of the beam, we've got a shear force value of minus 77.5. That tells us the gradient here is going to be negative 77.5. And what we have to do is to draw in a line of some description that will join those 3 tangents in one go. How you do that is you essentially draw on a curve that follows those tangents. To do that, you would start off with a positive gradient, coming to a maximum value. Then from that crossover point we would continue on all the way down until we come to the very end. And that is your bend and moment diagram for member BC. Now we're going to consider the next joint, joint C. So as you can see, we've got member BC, the end condition or the end loads, got a vertical force of 77.5, horizontal force 35, moment 45 kilonewton meters. Remember from the very start at joint C we had a horizontal load applied that was 20 kilonewtons. To take our end condition of member BC, we're going to transfer that into the joint by doing equal and opposite. So 35 kilonewtons going to the left becomes 35 kilonewtons going to the right. Vertical force going upwards of 77.5 becomes a downwards force of 77.5. A clockwise moment of 45 becomes an anti-clockwise moment of 45 as well. Now we consider equilibrium of the joint. So the joint here must balance. The net result for looking at the horizontal forces, 35 to the right, 20 to the left. So to balance that we need a force of 15 going to the left. Vertically, 77.5 going down, therefore we must have 77.5 going up. Moments, anti-clockwise moment at the joint of 45, therefore at the next connected face we must have a clockwise moment of 45 to balance it. These three red forces, moments, will then transfer into the next member CD. Equal and opposite, so the 15 going to the left becomes 15 going to the right. Vertical force 77.5 going up becomes a vertical force of 77.5 going down. Clockwise moment of 45 becomes an anti-clockwise moment of 45. Now taking these three forces in blue, we can take that with the force that's applied on member CD and draw out that and consider equilibrium for that member CD. Now considering the last member CD, the forces going into the member, 77.5 to the right, 15 going up, anti-clockwise moment of 45. Now on this member we have one load which is 15 kilonewtons in the middle of that member, and attached at point D we had a roller support, and back at the very start we worked out that the reaction VD was 77.5 kilonewtons. Now we consider the forces on our member of the beam. So looking horizontally, you can see that the beam indeed is actually balanced, 77.5 going to the right. At the very end, our VD force, 77.5 going to the left. So those two balance. Looking vertically at the forces, we've got 15 applied at point C, 15 kilonewtons going down in the middle of the beam. Indeed, that is balanced out to give you 0, so it's vertically it's already balanced. Then we'll do our moment calculation. So we'll add in a moment, we'll just add in a clockwise moment at the M and do our last equilibrium equation, taking moments about a point. Remember, our moments are force by distances. And we're going to take moments about point C. At the left hand side we have a moment applied which is 45. It's going anti-clockwise, therefore it's going to be negative. The 77.5 and the 15 are applied at point C. Distance offset is 0, so they don't produce a moment. What we do though have is the 15 kilonewtons applied in the middle of the beam. The distance from point C across to the 15 is going to be 3 meters. The 77.5 at point D, it is applied at point D but acts through point C. No offset distance, won't produce a moment. And then we have our moment on the end. The way I've drawn it in is clockwise, so I'm going to add in a plus m. Now considering the 15 kilonewtons in the middle of the beam, clockwise or anti-clockwise moment, right, put the force on a piece of string, allow it to freely rotate around your point, so you hold it at point C. How would the 15 kilonewtons want to rotate around? It want to rotate around in a clockwise manner, therefore it will be a clockwise moment. Work this out, minus 45 plus 45 plus m equals 0, which gives you the moment at the end to be 0. With the roller support we had at point D, it can only take force in a vertical direction, can't take any moments, so that checks out to be true. Now we can draw the beam out again and apply our loads and draw the first of our two diagrams. I've redrawn out our beam just with just the applied loads, drawn in some construction lines to help me draw the shear force diagram. Remember, the units for the shear force diagram are going to be given in kilonewtons. I'm going to start off our shear force diagram on the left hand side at 0. First force we come to is the 15 going upwards, and that will cause us to jump up to a value of 15. Moving across the beam to the right hand side, our forces, net forces, stay the same at 15 until we come to the middle of the beam, and the 15 point load will cause us a drop of 15 to bring us back down to 0, and for the latter half of the beam the shear force value stays at 0 until we get to the end of the beam. Now we're going to draw our bend moment diagram. Before we need that, we need some areas on our shear force diagram. To do that, we need that screen area. Quite simply, the area is given by the length by the breadth, 15 tall, and it's going to be 3 meters in distance. That will give you 45 kilonewton meters. Drawing some construction lines. Going to put in a 0 line. This will be our bending moment diagram given in kilonewton meters. Going to be starting off at 0, and on the left hand side we have a moment applied anti-clockwise 45, and that will cause us a drop to minus 45. Then consider the total area we have on our shear force diagram by the time we come to the middle of the beam. So by the time we come to the middle of the beam, we're currently at a value of minus 45 at the start. By the time we come to the middle of the beam, we've got a positive 45 area, green area, to add to it, and that will give us a net value of 0. That continues as there's no more area on the shear force diagram. That continues all the way to the very end to give you 0. Now we've got 2 points to join together, and what we do is we look at the value of the shear force, which is constant at 15, and that tells us the gradient of the line in this region, which will be a straight line of gradient positive 15. And that's the last of our shear force and bend moment diagrams drawn. Now we're going to try and draw the 3 of them together, overlaid on the original diagram. Now, as a final result, I've drawn a sketch of the initial framework and compiled together the 3 shear force diagrams that we had. Originally, the one in green for member AB, the one in red for member BC, the one in blue for member CD, bringing them all together onto one diagram. Next will be similar for bringing together the 3 bending moment diagrams. Now, bringing together the 3 bending moment diagrams, all the units are going to be in kilonewton meters. We've got in green the bending moment diagram for member AB, in red the bending moment diagram for member BC, and in blue the bending moment diagram for member CD, bringing them all together, superimposing them over on top of the original framework, and sketching or annotating the diagram with key values. The last thing to do is to sketch the deflected shape of the beam. On the left hand side you can see a simple sketch in black, and superimposed upon that is a sketch of the 3 bending moment diagrams that I've drawn earlier. To do the deflected shape, first of all you have to mirror image the bending moment diagram. To do that, pretend there is a mirror on each of the members and sketch in the shape of the bending moment as though it was mirrored about each of the members. First one, member AB, flip that over. Likewise for member BC. And likewise for member CD, we'll mirror that over, so it should look something like this. Try now to join or connect the 3 bending moment diagrams, or the inverse of the bending moment diagrams together will give you an indication of the deflected shape of the beam. Again, this is only a sketch, but it kind of gives you an idea of how the structure would actually deflect upon with the applied loading. Then finally, to do this deflected shape, in green is a sketch of the 3 bending moment diagrams, in red is a sketch of the 3 inverse or the mirror image of the 3 bending moment diagrams. Then finally at the bottom is kind of my best attempt at trying to connect the 3 bending moments together to give a deflected shape for the structure. The inverse of the bending moment diagram gives you the shape that any one of the members would take upon with the applied loading. And I've tried to connect the 3 bending moment diagrams together so you get an idea of how it would deflect with the applied loading.